Hello, we are Team 10 and our project is creating a parts measurement system. Our facilitator is Dr. Wen Lee in the back of the room. Our team consists of all electrical engineers and my name is Jared Jones.
My name is Eric Marks.
Justin Waltz.
Nolan Boya.
Mark Bolzhauer.
Today we will talk to you a little bit about, I will talk about the introduction of our project and kind of the background and research we did. Then Eric will talk to you about the conceptual designs that we came up with. Nolan will talk to you about the final design that we have. Justin will talk to you about the system components we're going to use. Eric will again talk about the risk analysis, and Mark will wrap things up with the project management plan and our budget. First off, our sponsor is Fanson Controls and Engineering. They're a local company out of Mason, Michigan, and they install manufacturing machines and control systems. They currently have a project working with Legends Manufacturing out of Jackson, Michigan. And here at Legends Manufacturing, they make these transmission valves for automobiles. We have a few parts we can pass around to you. What it actually happens is one of these parts, you can see when you get it around, is a solid part. It actually goes into a machine where it drills a hole in one end of it, and then it cuts a broach through it so that there's two slots around the outside circumference of the part. We need to create a automated measuring system for all these different parameters, and that being the overall length of the part, the depth of the end hole, the diameter of the end hole, and to check that there's just a single broach or two little slots around the circumference. The current process, actually, this is a picture of the end of the machine where our process will take over. Parts come out of the machine and they go into a wash tank where somebody then gathers the parts and brings it to a group of quality control personnel where they make these measurements by themselves. The problem with this process is a lot of times the parts don't get measured until a few days after they're actually manufactured. So if there's a problem with the machine and you're manufacturing bad parts, you can sometimes manufacture hundreds or even thousands of bad parts. And also there's always the possibility of human error when you have humans measuring everything. Our design will help eliminate these problems because we're going to have a real-time feedback to the machine operator, letting them know if bad parts have been manufactured and eventually stopping it if you have multiple ones in a row. This way, at most, you'll have 5 to 10 bad parts in a row instead of hundreds, and it will eliminate any human error. The requirements of our project, as I said, to accurately measure all the specifications. These are the actual numbers that we have to keep between. It needs to be transportable in case they move the machine or want to move our assembly to a different machine. It needs to be accessible in case anything goes wrong or there's a part jam. It needs to be easy for the operator to fix. It needs to have around a 7-second cycle time since we'll be receiving a part from the machine every 7.5 seconds. It needs to have safeguards on all the moving parts to ensure the safety of the operator. It needs to have the ability to be controlled by a programmable logic controller and a human-machine interface, all while staying within the $15,000 budget of our sponsor. A little bit of background research we did was we actually toured the Legends manufacturing plant, and we got to see the current quality control process with the people measuring all the parts. And we actually saw one of their fully automated measuring processes which used a robotic arm and 2D lasers. The only problem was this is a little out of our budget for our project. We also obtained a sample control box where we got to see the different sensors we'll be using, the PLC and the HMI. So we got to kind of learn how to interface between the different sensors in the PLC and the HMI. Then our first step for coming up with our design was we all, on our own, came up with our own designs, met together, and kind of compiled all our ideas to come up with a few conceptual designs. Now, Eric will talk to you about the different conceptual designs we have.
The team developed many designs to complete the project. The first design involved 2 displacement sensors. This measured the overall length of the part, a minimum diameter gauge, and a slightly larger than maximum diameter gauge. And how this works is if the minimum gauge cannot fit into the part, then that means that the part diameter is obviously too small. If the minimum gauge fits into the part end hole and the slightly larger than maximum diameter gauge does not, then it's a good part because it fits within specs. And if they both fit into the end hole part, then that means the diameter is too big. That also measures the end hole depth as well. And then there's the one-dimensional camera, which would measure the number of broaches at the end hole. And the reason the team didn't choose this design was because it's inefficient and has more stations than necessary, so it adds more complexity. Design 2 is 2 displacement sensors, again for measuring the overall length, and then getting a 2D dimensional camera to measure the diameter of the end hole, the depth of the end hole, and the broaches. The problem with this is it's very expensive. The 2D camera can be between $7,000 and $15,000, and so we didn't want to have that in our budget. And design 3 uses 3 displacement sensors, each with different tips. Each tip measures a different part of our piece, and that's what we're using for our final design. And here's Nolan Boyd to talk about that.
All right, for our final design, as Jared described earlier, there's 3 measurements we need to do on the piece for it to meet specification. So for the first one, which is the total length measurement, we are going to use a single proximity sensor, and we're actually going to modify this proximity sensor to measure displacement. Here's the unit right here that will measure displacement. This is going to be the proximity sensor, and it's going to be mounted to a machine part that has a spring and an end to it. Now, as this spring is depressed, this will measure how far it is displaced. We're going to have the entire displacement sensor actually mounted onto a slide, and the slide will be controlled by a motor. The motor and slide will move this way into the part as the conveyor belt goes up this way. So as the conveyor belt moves up and moves into position for the sensors, it will stop, and then the motor will push the slide into the part. Now, as the slide slides into the part, it's going to move to a predefined location. Now, this predefined location, we're going to know the exact distance from this location to the backstop. Now, after we have that distance, that's just going to be a constant. All we need to do is add the displacement reading from the sensor, and that will give us the total length of the part. So if we know that the slide moves a distance of 4 inches from the backstop every time, then we can add the displacement reading, and if the displacement reading is a 1/2 inch, we'll have a 4.5 inch part. The next measurement we need to do on the part is the interior diameter. Again, we're going to use another proximity sensor. It's going to have a modified tip to look more like a cone. And again, it's going to measure displacement. Now, as that's inserted into the end hole of the part, it's going to read displacement. And if the diameter is too large for the part, then we're going to have a very small displacement, and we'll know it's not within range. And that will be determined in the PLC. And again, if the diameter is too small, then we'll have a very large displacement, and we'll know that the part's diameter is too large. The last measurement we need to do on the part is the end hole depth. Again, we're going to use another proximity sensor, modify the tip again to look more like a needle that will easily fit inside the end hole. To measure this depth, we're going to add the part length, which is calculated 2 steps before, and we're going to subtract the distance from the backstop plus the displacement reading. That'll give us the depth of the end hole. These proximity sensors have an accuracy about 1/1,000,000 of an inch, so they're well within the accuracy necessary in our project requirements. And after the readings are all taken from these proximity sensors, they're going to be sent back to the central control unit, and we're going to use PLC to determine if all the specifications are met. And if any of these specifications fail, then we're going to have an actuator actually push the part off the conveyor. And now Justin's going to talk about the system components.
Thank you, Nolan. We're going to use the Allen Bradley Micrologix 1100. It's a PLC. It's this processor unit. It's expandable up to 4 cards, so that will give them the ability to add if they want to add any components to the system. This has a 10 input, 6 output base units, and it also has a 2 analog input channel. So that'll give us some additional inputs and outputs for our system. It's programmable using LadderLogix. This is Rockwell Software RSLogix 500. We have the ability to get this for free, so it's easy for the whole team to download this and use it to program the system. What it is it's a LadderLogix based programming system where if this is true, it'll turn on an output. You can do ANDs and OR gates. It's easier to lay out for control engineers to monitor what the system is doing. It is Ethernet IP communication based, It's going to connect to a switch, and the switch is going to connect to a personal computer that's in the front office. This will allow them to have a real-time feedback of what the system is doing. If they have bad parts, if they have good parts, how many parts they ran, how many parts they ran per hour. They can manipulate that data to view what they want to view for this machine. Robustness, the system is going to be placed into an oily and gritty environment, so we have to make sure that it has the ability to have a long lifespan for our system. So its robustness is very well, which will give us a good lifespan for controls. We're going to use a Seymour MicroLogix 6-inch touch panel. That's this. It's going to give them a colored 6-inch touchscreen where the operators will be able to have an interface to the machine to see what the machine's doing. It'll give them direct feedback from the machine to tell them whether or not their parts are in spec, their last few parts that have gone through, and what they can change this value depending on what their specs are put in their spec sheet. This is programmable as well. This is object-oriented based programming and reads bits from the processor or reads analog data from the processor. The way it communicates is a 15-pin D-sub RS-232 communication to the processor. This will give us the ability with this to monitor everything that's going on with the processor. This also has to have a high robustness for our environment. They currently have these systems, these touchscreens implemented at Luscious Manufacturing. They haven't had any problems with them yet, so they decided they want to stick with these. Servo motors. Servo motor, what it is a motor that has a gear reduction ratio. Pretty much what it is it turns on and continues to spin until it hits a certain set point. So it has a feedback loop with an encoder that goes onto the motor, and that goes back to the motor to tell it that it's got to continue to spin until it reaches a certain set point. Another motor that we're going to use in our project is a stepper motor. This is a DC brushless motor. It turns on poles using DC currents, and as the poles fire, it will rotate your stepper motor to an exact position. Servo motors, they're pros. They have closed loop position control. This gives them the ability to have exact position movements. They have the ability to move to a certain position within 32 or within a certain step or a certain degree. They have a higher torque capacity. They have the ability to move something back and forth with a higher rating than a stepper motor. The con is that they're very expensive. You need to buy this module. You have to have the stepper motor. You have to have the encoder cable as well as the encoder. You have to have an interface to your controller. You have to have an interface to each of these different parts of your body. So that adds into the cost of the project or of the motor. Stepper motors, they're pros. It has the open loop position control, so that lowers its expense down. Pretty much what it has a power supply. That's a 24 volt / 5 volt DC power supply. The 5 volts controls the unit itself, and 24 volt is what it sends out to the stepper motor. And so as you can see, there's fewer parts in the stepper motor, so it creates an expense that's easier to maintain. The cons, though, is that it does have the open loop position control. If you have any slip on your motor, you won't know it by feedback. You won't know that your motor has actually slipped up. And these are only limited to certain capacities. You have to match these up almost exactly to your project. So they won't have the ability to move this motor to another project if they need to, or they won't have the ability to move this to somewhere else. So both of them have goods and bads. We've decided that we're going to use our servo motor to control the sensor slide. That'll give us an exact position placement for our sensors. We'll know exactly every time that it's hit a certain position, every time that it's pulled back. We're going to use the stepper motor to control our conveyor belt. We don't feel like we're going to get a lot of slip on our stepper motor conveyor belt, so that'll allow us to have precise indexing. We're also going to have a digital signal feedback loop that says that the conveyor has reached its position, which will lower our cost down immensely. Now Eric's going to talk about the risk analysis.
There are many things to consider when designing this project. One of the big things is the cycle time of the cutting machine, because this time dictates the entire pace of our conveyor and digital sensors. If it's faster or slower, we need to account for that in the speed of our conveyor and the speed of the sensors. Another major risk is the consistent part placement. As the piece comes onto the conveyor, it has to go in between cleats. If the cleats are either too close together or too far apart, it could cause some errors. If they're too far apart, then there's too much movement in between the cleats where the part can have variation, and if there's variation, then you can't have complete accuracy when measuring the part with our sensors. And if the cleats are too close together, then there's not a 100% guarantee that the part is always going to make it into the cleat as it enters the conveyor. And then another major risk is the conveyor needs to be portable in case the people at Legends would like to do the measurements at different locations. It's important that it's lightweight, stable, and durable, so few people have to move it. Also, if there's some incidental contact that the conveyor just won't topple over and break or anything like that, it needs to be very stable. And also needs to be durable in case anything were to drop on it, or in a manufacturing area there's always risk, and so you need to make it so that any minor contact won't damage the conveyor system. And here's Mark Holzauer talk about project management.
All right, so I'm sure as you guys have been working on your project, you found that communication, clearly defining everyone's roles, has been an important part of the project. So I'm first going to talk with you guys about how we've defined our roles on the team. Nolan is in charge of document preparation, and technically we have assigned him the position of designing the sensors that will be used. He talked about them in our final design. There's 3 different sensor heads that are used with the displacement sensors, and so he's going to be designing the exact measurements of those sensors and getting them to the machine shop for them to be made for us. Myself, I'm in charge of project management, and I will also be doing the PLC programming. So I'll be the one helping to create the ladder logics that Justin talked about in the system component section. Jared is in charge of preparing our presentations, as well as leading the system integration and testing phase. So when it comes to integrating the sensors with the PLC and coming up with an efficient testing method where good parts will fall off the end of the conveyor belt into a good parts bin, and bad parts will be removed from the belt with other rejected parts, he'll be in charge of coming up with a good way to test that. Eric is our webmaster, and I don't know if any of you have seen our website yet, but he's done a good job with that so far. And he will also be in charge of developing our human-machine interface. So he'll be working with the object-oriented program, setting up the touchscreen interface. And then Justin is our lab coordinator. So he'll be in charge of ordering all the parts, which is good because outside of school he works with the sponsor a lot. And so it's a close interaction to make sure we get all our parts ordered on time. He's also been in charge of the conveyor system design. So he kind of led the charge for designing the exact specifications, like the belt width, how far apart the cleats need to be, the width and size of the cleats themselves, stuff like that. Next I'm going to talk about our timeline with the project. So we kind of split our project up into 4 main phases, as you can see. It kind of lines up there with our simplified version of the Gantt chart. The first phase is project definition, where we kind of met the team and we had a few meetings to make sure we had a clearly defined scope of our project. And from there we did a research phase, which is what Jared talked about when we went to Legends Manufacturing. We looked at the current processes, both manually and also the automated processes, so we can kind of see what to aim for, as long as it's still within our budget. Thirdly is the design and control integration phase, where we'll be designing the sensors, integrating the sensors with the conveyor belt, and integrating that whole system with our PLC and HMI. Finally will be the product testing phase, where we'll make sure that all good parts make it through all the sensors and fall off the end with the other good parts, and rejected parts will be removed from the belt using a solenoid. Lastly, I'm going to talk about our budget. As Jared mentioned earlier, we have a pretty increased budget compared to most groups. Our sponsors allocated us $15,000 if necessary. This is mainly because the system itself is very complex and there's a lot of very expensive components. So we have a very detailed budget that had a lot of items in it, so I just kind of picked some of the individual items that stood out with having a high cost. So the conveyor belt system itself is going to cost about $1,300 because there's a lot of detailed specifications that come with making a customized conveyor belt for our system. We are going to allocate MSU's funds towards helping us purchase and build a control panel. And you'll see items like the microprocessor, $600, the various sensors and the equipment that needs to be manufactured to hold them in place. It costs around $800. And there's a whole list of other components that add up to just under $2,000, as you can see. So all in all, this budget that we came up with should keep our project under $6,000, which is great because although they allocated $15,000, we'll save around $9,000 under that budget limit, which is good for minimizing the cost for our sponsor. So yeah, we've gone over our final design, and if you guys have any questions, we'd love to take them at this time.
Thank you. Other questions?
Mike?
So if you guys have an error from your cutter machine, will you see that like consistently? It'll just start punching out like 20 in a row that are bad.
Yeah, so that's kind of what the big problem is now. Is usually when it makes a cutting error, it happens consistently, and it sometimes can take them a couple days to get to the quality control process where they manually check all these specifications. And so if there is a consistent error, it could cut a couple hundred parts or even a couple thousand, depending on how much they're producing that week. And so this will allow for real-time feedback to prevent that from happening.
Okay.
Yeah.
About how fast do these parts come off of this machine? How long do you have to measure?
They come off every 7 seconds. So we'll be moving them along, and you saw the 3 sensors are on the same slide belt. So how we're planning on doing it is each individual measurement needs to be done in under 7 seconds, but we'll have it so that while all 3 sensors move in at the same time, there should be 3 different parts that are being measured at the same time, so that all of the measurements don't have to be done in 7 seconds, but just an individual measurement has to be done in 7 seconds.
Other questions?
You said like the environment is oily and everything, and these parts are being cut, and from what I saw, you have to hit like a half a thou tolerance. So are you cleaning the parts after they get cut, or is there going to be oil that could affect the measurement?
Yes, we're also implementing a wash blower system at our conveyor. The parts are going to slide under the conveyor to the little housing unit. And in that housing unit, we're going to do a glow station and then a coolant or a mineral spirit wash station and then another glow station before it gets to our measurement system. That'll wash out the parts.
So yeah, like our belt, we're ordering the total length is going to be around 4 feet, because down the road, our sponsor is going to want to implement that the flush blow part of it on like the first half of the conveyor, and so all of our components are going to be kept within the second half of the conveyor essentially. But we'll leave that first half open for our sponsor to implement that stuff down there.
How fixed is that back plane that you're pushing the part in?
Yeah, it's going to be mounted to the conveyor, so it's not going to move at all.
Okay.
Yeah, Mike?
Does your processor, are you guys able to implement your system to tie back into the control system of the cutting machine to
Yes.
get like active feedback to reduce errors?
Yeah, because they're all Ethernet communication enabled, we can put them all into a switch, and each one of them is going to have an IP address. For example, 192.168.0.1 will be our system, and then theirs might be 0.2. So they're going to be able to communicate back and forth to each other through that switch, through Ethernet IP communications.
Okay.
Yeah.
Is that Ethernet on their side already set up? So all you have to do is just apply their API to your whatever your protocol you're using, or
Yeah.
apply to their protocol?
Yeah, most of it's done through RS Links. Is their product is Allen Bradley, or is a Rockwell software protocol for Ethernet communications. RS Links single node is what we're going to be using. The sponsor is going to provide that to us on their laptop, and we'll be able to communicate between each system using that protocol. And it's pretty user friendly. It's easy to set up. Nothing like MSC Lens.
Anything else?
Thank you. See you Monday after spring break.
System has a lot of yeah, I was gonna say